So I wanted to take a look at a problem looking for critical numbers. This is one of those commonly missed questions. Here's our function. F of x is the cube root of 5 minus x over x. Just as a quick refresher, a critical number is defined as a critical number of a function f. It is a number in the domain of f, so that, let's call that number c, so that f prime of c equals 0, or f prime of c is undefined. We're going to come back around to that because there's some subtleties to that, the way that's phrased, that we're going to come back around to. But for now, we're really interested in looking at derivatives and all of that, so let's do that first. So f of x is this, and so I want to rewrite that as a big power. Radicals are never nice to look at. It's always easier to work with fractional powers. So f of x is 5 minus x over x to the 1/3. We could send this 1/3 through and look at this as 5 minus x to the 1/3 over x to the 1/3, because powers distribute over multiplication and division, and then use quotient rule. That's not really saving any time. It's really making things worse in a way. I'm not going to do it that way. The algebra works out much nicer if we do it with the chain rule. So that's 1/3 5 minus x over x to the negative 2/3 times whatever the chain rule tells us. Chain rule is the derivative of this inside, so bottom times the derivative of the top, it's just a -1, minus the top times the derivative of the bottom, which is just the 1, all over the bottom squared. Well, that's not terribly nice to look at, but we can work with it. There's a few ways of going about this. The way that I tend to prefer is, let's simplify this. This is fractions. Apply the negativeness of the power there, which would correspond to a reciprocal. And I am going to distribute the powers at this case, at this point. So that's x to the 2/3 over 5 minus x to the 2/3. That numerator is a -1 minus 5 plus x. Do be careful with subtracting in the quotient rule that you get all your signs right, over x squared. And we can see a little simplification happening with that x and that x down there. It's 1/3 times, so that'll be x to the 2 minus 2/3, which will be 4/3. There's also that 5 minus x to the 2/3, and that's x minus 6 up there. And so if we're looking for f prime of c is 0, and when f prime of c is undefined, conveniently enough, that when you have one of these factored simplified functions, that numerator is going to be, when the numerator is 0, it's going to make the whole thing 0, and so f prime of 6 equals 0. So we don't care about f prime of 0 at the moment. F prime of 6 equals 0, because that top is 6. Likewise, down here, we look at when you have this in this factored form, you can immediately spot an undefined derivative by division by 0. So that's x to the 4/3, although really it doesn't matter what x is raised to. If x is 0, this derivative is undefined. So f prime of 0 is undefined, and f prime of 5 is undefined. So according to this definition, our critical numbers, C n I'll call them, are 0, 5, and 6, except not. It's true that all three of these satisfy one of these two conditions, but there's this in the domain caveat there. And this is a bit of a technicality and a little frustration of how the definition's proposed. But if it insists on the number being in the domain, f of 0, if you look up here, you got division by 0 there. So technically 0 doesn't count as a critical number. It's still a spot increasing, decreasing can change. It's still a spot that maybe even you have a minimum or a maximum. Actually, it can't be a place where there's a minimum or a maximum, because In this case, at least, it's an asymptote. But it still places increasing and decreasing will change. So you will need to pay attention to that 0. 0 is important. It just doesn't fall under the official terminology of critical number. It's an annoying technicality. So our critical numbers are just 5 and 6. If we're interested in identifying these local extremes, like the second half asks us to do, well, we can do that. So we have our f prime of x. Let's just rewrite that. F prime of x is 1/3 x minus 6 over x to the 4/3, 5 minus x to the 2/3. And really, to identify with the critical numbers, we have two options. We could look at increasing and decreasing. We use the first derivative test. And look at f prime, and look at that 0, at that 5, and at that 6, and figure out up, down, or we can look at f double prime. We don't have to do the number line thing for f double prime. We just have to find f double prime of 5 and f double prime of 6. And if we get something like, oh, f double prime of 5 is positive, then we know the curve does something like this. And so that must be a minimum. And likewise, if it's negative, that must mean that's concave down. And so the only way you can get that is with a positive. I don't know if these are the actual values or not, because I'm not going to go through the work of finding f double prime, because this is a mess. It's not worth it. Plus, if f double prime worked out to be say 6 were 0, it would be inconclusive. There's an annoying thing about the second derivative test, that if you get a 0 second derivative, it can't tell you anything. Anything could have happened. The reason for that really is that, for example, if we look at x cubed, if that's our f of x, f prime of 0 is 0, f double prime of 0 is also 0, and it's not a min or a max. But if you've got x to the 4th or negative x to the 4th, you get the same thing. You still get a 0 derivative at 0 and a 0 second derivative at 0. But here we got a minimum, here we got a maximum. The curve's too flat for the second derivative to work. And so it's just not sensitive enough. So for all those reasons, second derivative test is usually more trouble than it's worth. The only time you really need it is, the times it comes into its own is if the f prime were simple, and so doing second derivative is not a pain. Or maybe it's a problem where they only told you f double prime and f prime, and they don't tell you what the original f was. In that case, you kind of don't have a choice. Either way, this is not worth it. Let's just look straight at f prime, at increasing and decreasing. All right, we got to be plugging in values, so f prime of something over here, let's say 10, it's going to be 1/3 times 4. I plug in the 4 there, but all I really care about is positive. Over 10 to the 4/3, well, that's a positive number, because I don't know, 10 to the 4th is going to be positive. Cube root is not going to screw up positivity. And then this 5 minus 10, well, that's negative, but it's a negative to the 2/3. It's a negative to the 2 to the 1/3. And so that evenness of that power is going to make that even, so the whole, or makes that positive, makes that whole thing positive. In fact, since that's 4/3 and that's 2/3, even an even numerator, that bottom's always going to be positive. I only need to worry about the top. All right, so anyway, positive, 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 the whole thing's positive. F double prime is positive. Or f prime, sorry, is positive there. So it's increasing. Let's grab something between 5 and 6. 5.5. Again, I don't care about the real values, I just care about the sign. Oh, I've passed 6. And so that top becomes negative, because it's something less than 6 minus 6. Okay, it was just saying that bottom's always positive. Between 5 and 6, it's negative. And to the left of 5, let's say 4. We could have picked a 1 or a 2, but again, I don't really care. That's minus from before, positive, positive, that's negative. And actually, that is going to continue on even to the left of 0. F of negative 10. Oh, write that up there. Is going to be 1/3 negative over positive times positive, so negative. There's a lot of decreasing here. From that, pluses and minuses, If I mark this, it's actually, I should have marked this back before because it keeps me honest and keeps me remembering. The derivative was undefined at 0. The function the derivative was undefined at 5. I'm looking back here. And f prime of 6 was 0. That helps remember whether this is a flat spot or a corner. It doesn't really matter for the critical numbers, the min and max, but if I was trying to graph this later, I'd want to know that. So our function f is increasing there, decreasing there, decreasing there. And I like to put a gap at places that I know there's going to be an asymptote where the original function had division by 0, and decreasing there. And so we get a minimum, we get a local minimum at x equals 6. If you really want to know the coordinates of that, it would be 6, the original f of 6, which would be cube root of 5 minus 6 over 6, so cube root of -1/6. And you can take cube roots of negative numbers. That's a non-issue. You can't take square roots, but you can take cube roots for negative numbers. So we got a local minimum at x equals 6, and looks like there's no local maxes. And that's entirely possible. There's no local max, and that would be the end of the problem. If you are curious what this looks like, we actually have a lot of what we can figure out. Assuming concavity doesn't get weird, I'm not going to worry too much about increasing, decreasing. That's exactly what I'm going to worry about. I'm not going to worry about intersections, intercepts. At 5, I actually know the original function has a 0 at 5, and at 0 we have this asymptote. I said that it's decreasing toward 5, decreasing like that, and then going up again. So that's my 6. I don't know if it actually goes off like that. In fact, it doesn't. It actually levels out. So there's going to be some sort of inflection point out here. But we can't tell that from just the first derivative. And then this goes up like that because of the division by 0. It's going to be decreasing down like this. So there's going to be a bunch of weird inflection points happening here. I'm not too worried about them, though, because that's not what the problem was asking for. All right, I'll stop there. Thank you very much.